kinetic energy at the beginning. We have potential energy. Like I said, there's no work being done from state 1 to state 2. And then we're going to have kinetic energy. That's the term that we're after, right? We want to know what velocity, how fast this block is moving, and how quickly this drum is rotating. That's what we're after. That's in this kinetic energy at state 2. And then we have potential energy at state 2. That potential energy at state 2 is going to be what's stored up in this spring, right? Because it's going to go all it's going to get stored up in the spring. It's an unstretched position here, and then it's going to get wound around there and get stretched out as it drops, right? I defined, again, I like to make my datum 0 at the bottom. That's why I have MGH on the left-hand side over here. If I put this down at y equals -4, this would be on this side as being a negative term, okay? And you'd have 0 on the left-hand side. But the way I define my datum, y being 0 at the bottom there, okay? So kinematics, you have to determine, y2 was easy. That's just going to be 4 feet, right? R times, I also need to, right? So sorry, I didn't expand it. So MGH, 1/2 mvb squared. So this is the kinetic energy associated with the block translating, right? I don't need the block rotating, so there is no 1/2 I omega squared for that block rotating. But then this drum is rotating, and there's energy associated with that drum rotating, right? So there's the drum rotating. This is the energy associated with this, 1/2 I-O omega squared. It's not translating, so I don't have to have the 1/2 mv squared for that term, right? So I got the energy associated with this dropping, and I got the energy associated with this thing rotating, right? And then, right, there's no other term. There's no translation or anything like that for those guys, or rotation. No rotation for this guy and no translation for that guy, right? And then it's all going into there's also going to be a spring there, which is 1/2 ks squared, right? So down into kinematics. Now, so right here, I got too many unknowns, right? I need to figure out what y2 is. I need to figure out how VB and omega relate to each other, and I have to figure out how far that spring has stretched, right? So y2 is 4 feet, so it drops 4 feet. R times omega, that's the relationship between how this point right here and also how this block moves and how this thing rotates. The relationship between omega and VB is just R times omega, right? That's the only thing you could do, and that's fine. Like I said, just taking a step from here over to here and using our kinematic relationships. But what you would determine is that relationship between velocity and omega is just R times omega, okay? And then how far does the spring move? This got a lot of you, right? If this thing drops 4 feet, this is on an inner diameter, right? That's on an inner diameter, and its diameter is half what the other one is, so it's going to drop half of what this one does, right? This one's going to coil around more because it's on the outside, and then this one's going to wrap around less because it's traveling less. There's a couple different ways of doing it, right? You could figure out what the theta is, right? Because the theta of the outside and the theta of the inside are going to be the same, and so that's what I kind of do here. I just show that, right? 4 feet is 0.75 times theta, so theta ends up being 5.33 radians, right? And then I take that radians and then I multiply it by the new radius, which is 0.375, and it gives me 2 feet. Or you could just look at it and say, well, it's half the diameter, so it's gonna do half the amount, right? So a lot of people just put in 4 feet for how that spring is stretched. I didn't dock a lot for that, but there was a little bit of a difference there because this one's on an inner radius and that's on an outer radius, right? Solving, at this point, we have all the components, plug in all your values, right? And then out pops 14.1 feet for my velocity. I solved in terms of velocity first, and then I actually didn't even solve for omega, but omega in this case would just be that divided by 0.75, which ends up being 18.8, right? So the combo was 14.1 and 18.8. Any questions about that one? Like I said, where people were messing up is, they were leaving off one of these. They were either leaving off this or they were leaving off this, right? Which makes the problem really easy if you do that, right? Because if you leave that off, then you don't have to come up with the relationship between R and omega, or V and omega, right? And then, or they'd leave off the spring down here, or they'd put the spring on this side, or they would, just sign errors and stuff. But like I said, it was 90%. You guys did great on this one. Yeah.
So the other option was to get VB in terms of omega R, but you kept VB and then just did VB divided by radius.
Yep, I could have done it the other way. I could have solved for omega first and then got VB afterwards. Yep, either one works. All right, and this is the extra credit. This is where I think some of you thought you had it, right? They thought you had it. And by the way, this is a really hard extra credit, right? This is a very hard extra credit because it was like what a lot of people did, and you guys thought you nailed it. You determined what Fs was. So that's the force in the spring. That would just be that K times the 2, because it's going to drop 2, and so they figured out Fs, and then they know the mass times gravity, and then these are our unknown reactions that were afterwards, and then they just went right this, and they said, oh, T is 300, because it's holding up a 300-pound mass, and T is 300. What happened is you dove into the statics world, right? In statics, it's 300, right? That's pulling on that, but the fact that if it wasn't moving, absolutely, right, it would be 300, right? Because this thing's mass times gravity and this thing, but it's not, it's moving, right? It's accelerating, it's dropping, right? So the tension in that cord is not going to be 300. It's going to be something else, right? It's going to be something else because it actually is dropping. So you actually have to do the F equals MA for this guy, then F equals MA for this guy, and then you get, just work your way through all this stuff, and then you have to come up with the relationship between alpha and this acceleration of this block down here, and then you work your way down there. That's what you end up getting, okay? So, like I said, a lot of you, we're almost there, except for you stumbled into statics realm, which we're not. Because it is weird, right? We've been trained all along, right? I got a 300-pound weight hanging from the end of this rope. Clearly, it's going to be pulling 300 pounds, but not if you drop it. If you drop it and it's falling, right? There's going to be tension in there. The only reason there'd be tension in that rope is because that rope is making this thing accelerate, right? It's making that drum accelerate. And so that drum lagging behind and being accelerated by the dropping weight causes tension in that rope, right? Because it wants to stay stationary. It doesn't want to move. But when it's dropping it, we got to get it moving, and it causes a force to do that. So that was that. Any questions about the extra credit? Got every one of you. Screw you guys. It's a competition. It's a competition. Trying to get you all. Okay. All right. This guy. Right. This guy, like I said, if I would have broken it down and looked at the scores for how many people got the first part right, what omega was, that'd probably be in the 90% thing. Where I got people was on the second one, right? I think this is a really fair problem because this is pretty close to almost identical, but easier than one of your homework problems, right? And then also pretty damn close to an example we did in class, right? The example we did in class, it had like a roller on the top, and then the thing was only going this. The difference, that one had a roller on the top, and then the thing was coming in just perfectly laterally. So this is added a little extra component coming down. This one was easier than your homework problem because I made this thing so small relative to this, and we said we could ignore the mass of this, right? It says in there somewhere. Yeah. You can neglect the massive A after impact, right? All right. Okay. And then I asked you please to do it because it makes your life a lot easier. Okay. So the thing is coming in. So first thing, right, we said to do these problems is you look to see if there are any forces acting on this thing or any moments acting on it. And it's not, right? It's out in the middle of nowhere, right? It's just floating out in space. You can think of it out in space somewhere, just floating in space, or like on it's just kind of a 2D problem, so it could just be like on a sheet of ice or something like that and just resting there. And then this this bullet comes in and it strikes it and it embeds it. And then your intuition should say that this thing is going to start moving down like this and also rotating up like this, right? So it's going to do both of those things. And the way we handle these problems, we kind of keep those things separate. Since there is no forces, there is no moments, we know that angular momentum is conserved because there's no moments, external moments causing, no external moments on this thing, and then no external forces doing this. So this says that angular momentum is conserved. This says that linear momentum is conserved because there's no external forces, okay? And in both directions. So, and then also there is no fixed point, right? There is no fixed point. So then we have to do our things about the mass center, right? We can't do it about this point up here because that's not a fixed point. If that was a fixed point, we could do it about that point up at the top, but it's not fixed, right? So we have to do our equations and our moments of inertia and things like that about the mass center, okay? So the angular momentum, about the mass center before the collision is equal to the angular momentum of the bar after the collision, okay? The angular momentum before the collision is just this particle. This isn't moving, right? So the angular momentum of the particle about the mass center would just be RA is seen from G crossed with MA times VA, right? So that's the moment of linear momentum, right? That's just the stuff before the collision. And then after the collision, right, it is just I times omega, because all we're going to deal with is that bar, because we're ignoring. Technically, there would be plus an R cross MAVA2 there, but I said that thing's so small, this is negligible in the overall solution, so that goes away, and so all you're left with is this, right? And the only unknown in there is what omega is, okay? So at this point, I need to calculate what my I is. It's just ML squared over 12. ML squared over 12. About 5 of you had the answer there of being 5. And it's because you divided by 2. It's because you don't know how to use your calculator. I figured it out. It's like, well, how the fuck did all these people getting 5s? And it's because when they're calculating, you fat fingered it, right? Right? I say use your calculator, but also use your calculator well. Right? The other answer that people got was 3.33, but that would be the moment of inertia about its end, which we don't want. We want the moment of inertia about its mass center. Okay? So at this point, we just plug in what this R cross MAVA is. So the moment arm is this. I wasn't too big of a stickler on signs. If you did it wrong down here, but still said that it came out as being a positive omega, I was fine with that. But if you said it was a negative omega, then I did dock you a point. But the correct way to do it would be to say that this thing, that is negative 0.25 in the J, because you're going to A from G. That's the moment arm we're using. 0.15 is the mass of A, and then the velocity of A, it is a vector, right? It's 100 times cosine of 30 in the I direction minus sine 30 in the I direction. A lot of people did that reversed, did sine 30 in the I plus cosine 30 in the J. That was a small deduction, but that was also geometry. I got you with the geometry. But that's it, right? So that's my R cross MVG. You just carry out this cross product. You get 3.25 in the K, and that's equal to 0.833 omega in the K. And the only unknown there is omega, so you get omega is equal to 3.9 radians per second. Like I said, about 90% of you got that right. Good job. Okay? But this is where I got the rest of you. So now we're trying to go to VP, right? I need to know what the velocity of P is, right? And we always start when you do this step, you always start out with a point that you know the velocity on your body. Right now, right, in this current, say, I don't know the velocity of anything, right? A lot of people tried to say that VG was 0 or that B was 0. Right after the collision, that's not the case. It's moving, right? It's translating because it's been hit by a bullet. The whole thing's going to translate to the side, right, as well as rotate. So there is no point on here where the velocity, there might be a point where the velocity is 0, but we don't know where it's at, okay? So we have to do conservation of linear momentum to determine what VG is, right? Linear momentum, the way it works, right? Mass times velocity, mass times velocity before is equal to mass times velocity after, okay? And then when the after part, this right here, the velocity you get after is not the velocity of where the bullet came in. It's not the velocity of this point right here at A. It's the velocity of the mass center. Right? And you're like, well, how is that? That's just the way we set these things up. We kind of keep them separate. We're kind of dealing with the translation part is about the mass center, and the fact that this thing is going to rotate is accounted for with the omega. Okay, and so you do the mass times velocity. Right? Mass times velocity is equal mass times velocity. You have components. Velocity of A has an X and Y component, so you leave it in there. So it's 0.15. Yeah, okay. Right, times. Yeah, 0.15 is the mass. The velocity of A, this should just be times. I don't know why I wrote it as a... 0.15 times 100 times cosine 30 in the I minus sine 30 in the J is equal to 10 times VB2. And so you got to keep the components of it, right? VB2 is going to have an X and a Y component to it. You have to keep both of those, right? So basically, whatever right, this thing's coming in at an angle, and so this thing is going to continue to move down, and it's going to translate to the right. It's going to go both of those things. Both the momentum in both directions are conserved. So you have two components there. So now I get that. That's the velocity of the mass center, the 1.3 in the I minus 0.75 in the J. So now I could take a step from VB2. I know what that is now. I could step from there down to VP with our relationship VB2 plus omega crossed with RP as seen from G. And that's what I do. 1.3 in the I minus 0.75 in the J plus 3.9 in the K crossed with negative 0.5 in the J. And this is what I get for VP. 3.25 in the I minus 0.75 in the J. Right? Cool. Like I said, there was a lot of deductions because one, they just assumed velocity of P was equal to 0, which isn't the case, and left out linear momentum altogether. And unfortunately, the way I set this thing up, right, that was worth 10 points was if you had the linear momentum thing. So if you didn't do any linear momentum, it was like an automatic like 8 that was off for that. So also several energies, right? Several energies for these ones. And there's no energy in this thing at all, right? Because there's no energy conserved across a collision. So, and I think some of it, and I don't blame you for it. I think what happens, they got to here, and then they instead of hitting linear momentum, they were like, I don't know what the fuck to do. And so they're like, I must have to do energy. And so they jumped over and did energy to try to fill the gap, and then just missed the linear momentum. So, no judging. Any questions about that? That's it. That's it for our quizzes, okay? Or exams. Right, it's 12.5% each, right? But we still have a big one coming up. Right? How much is that one worth? Is that 30? Oh, suck. That sucks, huh? Right? That's intense, yeah. Yeah, I think what I've done in the past is you could use all your previous note sheets in the new one. Yeah, that's what I. Did you throw yours away? What? Did you throw your previous one away? Oh, okay. But it is, like I said, it's gonna be conceptual for about a third of it, and it's multiple choice true falses, right? That's a third of it. And then there'll be 3 problems. One problem, a fairly easy problem from something 2D related, and then 2 problems, 3D kinematics and the 3D kinetics. Okay, and that's what it's gonna be. And we have 2 hours to do that exam. Yeah, it'll be a good time. Yep, I'll post 2 examples for the 3D stuff. Yep.
Will we be in separate rooms?
Nope, we're all going to be in Gaines. Gaines 101, I think.
101?
Yeah, I think that's what it is.
That's the big one.
That's the big one. I just need to make sure I got enough room to spread out to keep you cheaters in line.
Yeah.
I was wondering about all those answers, the I equal 5 thing. I was like, where did everybody get I equal 5? I was wondering about that.
We all cheated.
That's what I think. Yeah. It's just funny there's like 4 of you that are all stupid. No, I'm just joking. No, that all just made that same mistake. I was like, how the fuck? I was like, it's impossible for that propagate across a row, right? Like, no. You know what? In COVID stuff, yeah. Yeah, COVID stuff. COVID stuff, absolutely. Right, the Chegg thing, right? I'd post the solution, or I'd post the test, and within minutes it would show up on Chegg. But luckily it was always the wrong answer. And so then it was really easy to find the ones that you had that exact same wrong answer. Yeah. I had one where on the final where I gave it, and there's this whole bunch of people just started using like a nomenclature that we hadn't used before, and I was like, "What's happening?" And they'd found the problem that I got out of a textbook and copied the solution manual out of the textbook, but it was really easy to find them too because they were using variables that we didn't use, and so I was like, "I don't know where you got that."
Smarter about it.
Yeah. Okay, let's do this here. Let's finish this off. Yeah, be smarter about your cheating.
Yeah.
Don't work harder. Be smarter about how you cheat. Be smarter about how you cheat. And we're at a good pace here. We're at a good pace. Right, we're kind of done with the kinematics. You're working on a homework this week. Right? There's some intense problems. Like I said, I considered at least learning how to do it in your calculator. Okay, so we were in the middle of this guy. Let's just kind of quickly go through what we were doing here, right? We've got this omega, right? Rotating about the z-axis. And because that's rotating around, and this is a wheel that is not slipping right here, I know 2 points on this body where the velocity, or these bodies, where the velocities are 0. I know velocity at point C is 0, and I know the velocity at point Y is 0, right? Technically, right, you like to think of it being pinned down here at 0, 0, but they don't really give us a vertical distance. I guess they do. It'd be this distance right here. But the point is, it doesn't matter. Point C is also not moving, but the cross product would take care of the fact that this would have a little bit of component in the Z direction. There would be an omega in the K crossed with R in the K, and so those two would just go away. So that the K component doesn't matter. It doesn't play in at all. Right? But what we did is we took a step from here to the center, and we took a step from here to here, and then we set those things equal to each other, and out of that came a relationship between how this rotates relative to how this rotates. And what we determined was that one is rotating around twice as fast as the other. Right? Right? And then once we determined what that omega was, that omega that we found was the omega of this disk relative to the bar that it's rotating about. Right? And so then we had to add those two together so that when I'm out here on this, I have the omega that I found, and I have this omega as well, because it's rotating around that axis, but then it's also rotating around the other axis too. It's got two components to it, right? And then, so when we take a step on anything that's out here on this body, we have to take into consideration it has both those omegas. So we step from here up to here, right? And that's what we did. Right, this is what kind of went through that process. And then we did the same thing for accelerations, right? Or we're in the middle of doing accelerations, right? So there's the accelerations, right? Even though we had even though this was constant and that was constant, even though both of those things were constant, we still pick up an alpha because this thing is rotating and it's changing the direction in which it's rotating, which means there has to be an acceleration, and there's your acceleration right here. It's weird because it shows up around the x-axis. It's rotating about the y, and it's rotating about the z, but you pick up an acceleration about the x, right? Which is odd, but it's real. And you felt it, okay? And so then we made some steps around there, okay? The other thing I wanted to point out here, this is an important concept. I keep saying that you have an object that's rotating about another object, okay? Sometimes it's rotating within another object. Okay, and I know that throws people off sometimes. An example of one where it rotates within another object would be, this is one of your homework problems. Okay, this is a homework problem. And so what would you think the body is in this thing?
That's a homework problem?
It is a homework, isn't it a homework? It is a homework problem, right? Is it? Have you done the homework?
Sorry.
You did, but you didn't see this one? Oh, good for you. Good for you, yeah. Good for you. I thought it was. Okay, well, this isn't a homework problem, but we'll see it again. We'll see it again at some point. Okay, but this is one, right? What would you think the body is in this? So this is like a top, right? You got a little gyroscope. This is a gyroscope, right? And you get the thing in the middle rotating around. You set it on its end, and it kind of rotates around. What's the body in this case? The middle thing, right? Because this is what I'm saying. It gets a little confusing. I keep saying, oh, the thing that's rotating about the other thing that's rotating. Well, this is rotating within the thing that's rotating, right? So this is rotating like this about this axis, and that axis is rotating around, right? So just be careful of that. We'll see this one again. Let's see this one again. Don't be worried. If it's on this homework, you'll get it eventually. The gyroscope. Okay. All right, so back to this, right? So now what the last step where we left off right here is I was after AP, right? I was after this point, the acceleration at point P. And what I had to do first is I had to figure out what the acceleration of point G was. And then once I knew the acceleration of point G, then I could take a step to P. And so I just figured out what AG was, right? AG, I took a step from here to here using our acceleration equations, right? AG is AC plus alpha of the bar crossed with RGC. That's the tangential acceleration plus this double omega thing. And when you carry out that, we determine that AG is accelerating back towards the middle at R omega squared. Okay, so let's go to AG now. Now that I know, or sorry, AP. Now I know AG, I can go to AP. AP is equal to AG, which we just found, plus alpha of A. That's alpha of the body. Crossed with R, P is seen from G. Plus omega of the body. Crossed with omega of the body. Crossed with R, P is seen from G. Yeah, we're calling it alpha A. Yeah, that's the body. That has both the things in it. So when you're out here on that body, right, we have to make sure we're using the full alpha, right, the alpha of the body that takes into consideration the rotation about the rotation, right, that off-axis alpha. So we're going to have an alpha, even though our omegas are constant. Scared the shit out of me. I almost ran. I almost ran. Like, there's a bomb. There's a bomb, everyone. Yeah, yeah. And then these omegas that I use, those have to be the total omega as well because I'm out on that body, right? So this is actually, when this blows up on us, right? Blows up, yeah, blows up on it. Blows up. That's why the alarm went off. Like, holy shit, look at all this, right? AG, we just determined it was negative 2R omega naught squared in the J direction. And I add on to it, right, the alpha A, which is 2 omega naught squared in the I, and I cross that with RP is seen from G, which is R in the K direction, right? It's taking a step from here to here, which is R in the K direction. All right, R in the K, plus omega naught in the K direction, minus 2 omega naught in the J direction. That's just omega naught, right? And I have to cross that with the quantity of that again, omega naught in the K, minus 2 omega naught in the J. That crossed with R in the K. Right? I'm sure nobody will make mistakes doing that. That'll just be real smooth, no problems, right, with all those things. But this, like, honestly, this is where a calculator would be really nice. In particular for something like this, right? You're having this, right? You're carrying out this double cross product over here with all these terms. So you're carrying out this first, and then that'll give you 2 terms, and you have to carry that crossed with this guy, and then you're also crossing this guy, and then you have to keep track of all your I's, J's, and K's. Your calculator will do this just fine if you learn how to use the vectors with it. Okay? And I'm gonna skip down to the answer. AP is equal to negative 6R omega naught squared in the J minus 4R omega naught in the K. Okay. That'd be good practice for you, right? I mean, there's a perfect example where you can just pull out your calculator, you got the equation exactly the way you want it, and just see if you can make your calculator do that, right? You set these things up. This one would be, you know, in your calculator, this would be 0. The vector would be 0, negative 2R omega naught squared, 0, right? That's what this value would be, right? And then you just set up this one in the same way, right? It'd be 2 omega naught squared, comma 0, 0, crossed with 0, 0, R, right? And then you would set up different variables in your calculator if you wanted to, and then just let it rip. How many people use their calculator for these cross products? Okay. The rest of you are doing right-hand rule? Right-hand rule, just go to town? That's fine. That's fine. It works for you. Okay. This is what this problem would look like, just to give you a little heads up, right? This is what it looks like in MATLAB if you wanted to do it in MATLAB, right? I go through, I defined what this one I did, you have a little bit more complicated because you have symbolic toolbox. Did you guys learn symbolic toolbox when you did MATLAB? Yeah, how long ago was this for you guys? Yeah. A week ago? A week ago? Was it really? Yeah. Yeah, you do. Well, they're very similar to each other. By the way, you know what's really good at these things? ChatGPT. It is so good at doing coding. Like seriously, if you ever like in your Python class, you should have seen the video game I made in Python with ChatGPT. Never opened up Python before in my life. There's a game called, I swear, there's this game called Asteroids. I should bring it in sometime. You ever played Asteroids? It's a little ship that goes around and it shoots the asteroids and they break up into little pieces until you hit certain, and then you can move your ship around. So I was like, I want to create the game Asteroids. And so he goes, okay, here's some code, right? And just spit it out. But his first version of it, it's like, there's like all the boulders were like big like circles, and then my ship couldn't move. So I was like, just in plain like English, I just go, hey, can you make it so that my ship can move when I hit the space bar? And it goes, sure, right? And so then it gives me it's, you know, if you got into like object-oriented programming in Python yet, but it just goes and says, here, replace the section of code where you define the object, which is the spaceship, with this section of code. It didn't give me all the code, just a little, and I did it. I put it in there, so then when I hit the space bar, it moved. Right? But that was just like, that's great. But as soon as I let go of the space bar, it would stop moving. There was no momentum. So I was like, well, I would like to have momentum in my ship. So if I hit the space bar and the thrusters come on, and if I let go of the space bar, I want it to like keep going with the momentum. And so then it did it. It did it. And so it just, okay, here, replace it with this. And so then it did it. But the problem is so I put the thrusters, I had shape facing this way, put the thrusters on, and I'd go like this. And then I would say, I take the thrusters off and it would keep going like this. But then if I turned directions, my momentum changed without changing, which is wrong, right? So all I said to ChatGPT was, you know, I think